Hello, everyone. Good afternoon from Colorado. My name is Pengfei. I'm a research scientist from the Colorado School of Mines. Today, I'm going to talk about tectonic-sedimentary interplay of a confined deepwater system. This is part of my PhD work done at the Colorado School of Mines, sponsored by the Chevron Center of Research Excellence and the Sedimentary Analog Database Research Program. So let's get started. Okay. So just a little bit background. I think we're all familiar with submarine fan deposits and turbidites. There's a wide range of variability in the facies models of submarine fans. Part of that is because submarine fans are very sensitive to basin shape. If a fan can reach the edge of the basin, and we say it's confined, and there are four main types of confinement defined here. Namely, they're ponded, lateral confined, or frontally confined, or unconfined, depending on the relationships between the sediment supply and accommodation. In addition, submarine fans can also be strongly influenced by intrabasinal structures, as demonstrated in the examples here in the Annal sandstone or the Numidian Sicily. The challenge for working on these outcrops there are two main challenges. One is the relatively low preservation potential. The other is difficult in correlation because of the structural complexity. And the main question we want to answer in this study is how can we use the relatively fragmented outcrop data sets to best answer the relationship between tectonics and sedimentation. Okay, so we choose the study area as the Ouachita Mountains in the south central United States. The advantage of this study area is that it's a Paleozoic active margin. It has a long and relatively complex structural history, but also with extensive outcrops all over the basin, so we can grasp the facies characteristics from different locations. During the mid-Carboniferous, like late Mississippian, very early Pennsylvanian, the study area is situated in southwestern Laurentia, and that was a time during the collision of Laurentia and Gondwana before the formation of Pangaea. Locally, this basin is formed by terrain-continent collision because there's a lot of like peri-Gondwana terrains along the margins of Gondwana. And this basin just slowly evolved from a remnant ocean basin phase to a foreland basin before 300 million years ago. So if we zoom into the study area, it's over here sitting on the northern side of the Gulf Coast, the present-day Gulf Coast region. The Ouachita Mountains are the outcrop part of the ancient Ouachita Fold and Thrust Belt. So this area has been divided into three structural zones. From north to south, they are the continental foreland, which is the white, the orogenic Foredeep, which is the blue, and the yellow is the wedge top, or also called the Ouachita Allochthon. And the outcrop belts of the lower Atoka is marked by the dotted bands here. So the formation we're interested in is called the lower Atoka. It's about 350 million years old. It was a submarine fan deposited during relatively low sea level and high precipitation because it's in low latitude tropical zone, and high tectonic intensity. In the past couple of decades, there's been a lot of work done on the lower Atoka submarine fan system. In general, the basin at this time was a early foreland phase. The thickness can be up to 3,000 meters thick. The sedimentation rate is pretty high. It's on average 1,000 meters per million year. net growth 25 to 40%. The sandstones are very fine to fine-grained, submature. One other thing is the base from the representative models, we can see that the main sediment source is from enter the basin from the east, actually from the southern part of the Appalachian. So for the data set, we use 54 outcrops, and each one is a detailed measure section. We record bed by bed, thickness, grain size, sedimentary structures, paleocurrent, etc. For each one, for each outcrop. So totally we have over 2,500 meters of measure sections and over 11,000 individual bed measurements. And we group them into 18 composite sections. So on the map, shown on the map here, by comparing the composite sections with qualitative and semi-qualitative field observations from my field work and previous field guides and geologic reports, we think that each composite section is representative for the lower Atoka for this little area, for each area. For the methods, we first re-examine the structural and depositional zones for each zone, and we also updated the structural history by combining multiple versions of previous structural restorations and most recent geochronology, thermal chronology, and geochemistry and petrographic data. And so that's our update with the structural history, and we correlate each composite section to get a sense of what the main facies distribution of the fan throughout the basin. For facies scheme in this study, we use the 3-level hierarchy. Starting with beds, which are the basic. We define 6 types of beds based on sedimentary structures and thickness, and the beds are grouped into 5 types of lithofacies, from massive amalgamated sandstone to mudstone and to disturbed mudstone sandstone. And the facies are then grouped into 4 types of facies associations. These are interpretive stratigraphic architectures. They are channels, lobes, mudstone sheets, and mass transport deposits. Okay, and here's an example of how we interpret the facies hierarchy in an outcrop. We also compare our thickness range of lower Atoka channel thickness and lower Atoka lobe thickness with several other more famous turbidite systems, both in the study area and also around the world. And the purpose for this is to first see if our definitions are reasonable and consistent with other studies, and also to check what the so-defined channels and lobes in the lower Atoka, are they equivalent to like which hierarchy in other studies, and most likely it's equivalent to the element level in other studies. Okay, now let's take a look at the results. So let's Foredeep first. We can see here some outcrop photo panel examples. So the Foredeep, we can see we have data from all the way from east to west. And from the paleocurrents, we can see that the major axial fan system goes from east to west and all the way to S12 here. There's also a small, like marginal fan that goes from west to east, likely stops around S12. And for the facies compositions, we have like bad facies, lithofacies, and facies association level. We can see the longitudinal changes. There's a high variability, but in general, there's a decrease from east to west. There's a decrease in the sand-rich beds and and the channelization and net growth and amalgamation. And there's also a small decrease from the west to east all the way to S12, and that's consistent with the paleocurrents. And from the statistics, we can say the basic statistics of percent sandstone, amalgamation ratio, standard deviation of sandbed thickness for each composite section. We can see a similar trend, like proximal to distal trend. Comparing to the results in the wedge top, we have 5 composite sections in the wedge top, and the paleocurrents all show in general east to west with some local variations. And the facies trend, we can see the sand ridge components is relatively stable, although there's a local minima in S16, and it actually slowly decrease and increase again in the down deep region. So there's not a clear proximal distal trend like shown in the Foredeep. So just jumping in a discussion here, why is there a contrast in the longitudinal facies distributions in the Foredeep and the wedge top? And part of that is because this basin is not a classical multi-foreland basin. It's an early phase, so that the wedge top is not that prominent yet. They're both underwater. They're 2 parallel systems. And they have, if we look at the facies results by quadrants, we can divide the Foredeep and the wedge top into quadrants, and then just compare the proximal Foredeep and wedge top, and we can see the facies compositions are almost identical. That supports the idea that they share a common source. So sediment supply is probably not the reason, but meanwhile we know that the wedge top has more structures, more structural induced topographies, and that will result in a greater degree of confinement, lateral confinement in the wedge top, which supports sediment transport and bypass down dip, and that will result in a smaller contrast up dip and down dip, which is consistent with our facies trends. So, and this is also found in many other foreland basin systems, such as the Pyrenees, the Cilician foreland, the Magallanes. So this is not uncommon. So we can zoom in to the Foredeep, the proximal part of the Foredeep. It's actually a syncline called the Forge-Lava syncline. And we have the highest density of outcrops in here, so we can compare the north and south side, north and south limbs of this syncline. We can see from the paleocurrents here that there's not a big difference between the north and south, and there's also not a big difference between thick and thin beds like based paleocurrents. But for the facies compositions, we can see that the north side is more sand rich, thicker bedded, or more channelized and more amalgamated. And the south side is more stable and relatively thinner bedded. And the statistics we can see, especially if you plot the amalgamation ratio versus the standard deviation of sandstone thickness, we can see there's a good separation of the north and south. And we'll talk about why is that. And this is here's just a quick paleo location of this area against the structural restoration. So what's the reason for this cross-current asymmetrical facies distribution in this syncline? We have 3 candidate interpretations. One is axial or marginal fan locations. This is not likely for short distance, like less than 20 kilometers over a long time, because if it's a flat basin floor, over time, compensational stacking tend to distribute sediments more evenly, and they should show similar results in short distance. And number 2 is additional sediment supply from the north. We know that northern source is likely trivial, although there is. but it also needs, even though they can contribute to this syncline, but it needs additional barrier to prevent sediments coming to the south, but only restrain them to the north. So that's, but there's no evidence for that. And the last one is gentle structural tilting on the south side. This is consistent with our structural history, like shown on the previous slide here. And it's also analogous to many similar turbidite systems documented in Europe. And it also requires minimum assumptions, like no other assumptions based on Occam's razor. So that's our favorite interpretation. We're just going to take a quick look at the continental foreland here. The outcrop data are limited. Most of them are subsurface. We have two composite sections, S1 and 2, one on the north and one on the west. We can see that they have very different paleocurrent patterns, very different facies contrast as well. And we interpret them as controlled by the local sediment source and local paleogeographic configurations. Okay, so just in conclusion, so this study is a complete and quantitative documentation of lower Atoka submarine fan system. We emphasize the role of intrabasinal structures. We actually incorporate the structures into the facies model. We also incorporated the additional data, pretty much all data available in this area, especially on the basin margins on the west and on the north. And we show that there's a good consistency of facies distribution and the updated structural history. So our main interpretation for the distribution of facies is the main axial fan system coupled with variable degrees of lateral confinement across different places in the basin. And this work is actually impressed in the Journal of Sedimentary Research. I'll just thank you SEPM and ISGC for this opportunity to present my work. That's it. Am I good on time?
Thank you so much. Yeah, I think we have time. We're running a couple minutes behind, but I think we have time for at least one question before we move on. If anyone has one they'd like to ask. I don't see anyone's hand raised or any questions in the chat. Is there anyone, a last call for questions if you'd like to ask a question before we move on to our next speaker?
Hi, good day. I couldn't hand raise, I think. I really enjoyed your talk. I was curious, do you see overlap of your sedimentary systems with the growing thrust? Like on your
No,
top,
not,
for example?
Hi, sorry. No, not in my data sets because the reason is most of them are tilted outcrops, tilted road cuts. They're not laterally extensive, so you can't trace them like a long distance. However, there are some subsurface data on the near the foreland, continental foreland side. There are lots of evidence of overlapping with growing topography.
Thank you.
Thank you.